Hey there, welcome back to the channel. So we are back. I have a project in mind, and for that, I need to read some stuff. I'm tired of writing the C style C++. I like I use structs and write normal functions when I should be using object-oriented programming and template meta programming and whatnot. But okay, not that much, but I need to learn some basic stuff before starting with the project. Uh, I'll be reading this chapter first. I've completed everything above it, but I'm not going to complete the entire C++. I'm not going to read every single chapter line by line. Enums and structs, it's not going to be that useful for the project. It will be important. I can improve my coding style by reading some stuff from it, but it's just not worth it. So I'm going to read this chapter, references and pointers. Then I will skip over to maybe I'll read classes. Maybe there's another more on classes too. Maybe I'm not sure. Skip, 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 skip. Operator overloading. I have read about this in previous one of the chapters, I guess. This might be something in depth. Yeah, move semantics and smart pointers. This is going to be really important. So what our project is, I'm not going to reveal it, but it is something related to shared pointers. I'm not going to make my own shared pointer. I, it's, the the classic questions that we get in interviews, like implement your own shared pointers or implement your own unique pointers. No, not going to implement my own shared pointer, but this is something related to shared pointer. This is something related to like oh sorry, I was going to reveal some stuff. I'll reveal it later. But okay. Because I'm still looking at the feasibility of the project. Okay, I'm sorry I said that I'm going to look into it, but I'm still reading about it, reading some research papers, how some people have done that project. There are some research papers. I'm going to look into that too. So yeah, and do this. Then I don't think anything is that important. Templates and classes. I don't think I need template right now. So gonna skip that. Okay, skip, 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 skip. Boom. Let's just get started. So I read the first two or three chapters maybe, and I recorded the video, but I took a break and I just slept. Yeah, I went to sleep. I forgot that the video was still recording. I actually took a short break and then I just fell asleep. This look at this video. Look at this. Look at me reading this stuff, and then boom, boom, I'm gone. Yep, I'm gone for the entire time. Look at this. But okay. So let's get started. 3 minutes and 15 seconds, 3 minutes and 16 seconds. Okay. So let's get started. Where is it? Okay. I'm just going to minimize this because I like my OBS Studio in the rightmost window, rightmost window pane, planes, whatever. We'll start from the beginning. It's fine. It will be a small revision. So let's get started. Introduction to compound data types. So what are compound data types? Let's look into it. I'm audible, audible, audible. Am I recording, recording, recording? Okay, that's cool. Okay, so let's get started. In 4.1, we introduce a fundamental data. Oh, also by the way, this is not kind of like an alternative for Learn C++. This is not an audiobook for Learn CPP. If you want to read about Learn CPP, please go to the site. I will mention the site in the pinned comment or maybe description, whatever. Uh, Use that site, okay? Don't refer to my videos. This is the original content. 4.1 to fundamental data types. We introduce the fundamental data types, which are basic types, C++ plurals. Yeah, I don't think I need to read every single thing again, right? Okay, yeah, sure. So let's look at the code quickly. First fraction, second fraction, boom, num1, num2. Even though the two fractions multiplied, boom, and then the program. While this program works, it introduces a couple of challenges for us to improve upon. It's only loosely linked. Okay, don't repeat yourself. We should create a function to handle the user inputting a function along with some method handling. However, functions can only return a single value. Yeah, so our main problem is a function only returns a single value. Well, that sucks. So how should we improve it? Well, other languages have improved it. If you know about Python or Golang, so they have like they can return multiple return values. You just have to mention that. Like the functions are like okay, not gonna show it. But okay, that is a cool feature, but it's fine. No problemo. So now imagine another case where you are writing a program that needs to keep a list of employee IDs. And this, if you want to add more IDs, then you have to add ID 4, 5, 6. It is not feasible. Compound data types. C++ supports a second data type, compound data types, also called as composite data types, are that defined in the terms of other existing data types. Compound data types have additional properties and behaviors that make them useful for solving certain types of problems. What kind of problems? Well, they are a collection of other data types, or something related to the basic data types, you can say. Sorry. The following compound data types are functions, C-style arrays, pointer types, pointer to member, reference types, enumerator types, class types. Boom. Structs. We have already been using one compound data type regularly, functions. So this type of function is called void int double. Yeah. Note that this is type of composed of fundamental types, which is a compound type. Of course, functions also have their own special behaviors as well as being callable. Yeah, sure. And then we talked about increment. So let's say x plus x. This will increment the value of 5 to 6. And if you print this, it prints 6. That's cool. Uh, if you notice that I'm just skipping a lot of stuff because I've already read this. So since here there is auto, so like it is to be converted to some data type. So this is an int and this is an int. It will convert to int. This is a double. So we cannot do narrowing conversion. So for we won't convert 12.0, which is double, to 12 because that will be narrowing. So we have to convert 4 to double. So this will become double divided by double, and here v2 will be a double variable. Just give me a minute. Back again. So yeah, here v1 will be a int and v2 will be a double. Via type reference, int will be used as a type of v1, and here v2 will, so double is the type of this expression. Cool. So this is a print foo. Print was expecting an int, so foo, which is a C style string, it can't be converted to an integer, right? Like duh. If there was a char, maybe, but no. In the above program, the print int, yeah, fine. Value category of an expression. So int x is equal to 5. This is possible. 5 is equal to x is not possible. Why? Because of some stuff that we are going to read, and we can see some hints over here. So x is a variable. We can store stuff into the variable, but 5 is literal. We cannot store stuff. We cannot change the value of a literal. A literal is a literal. It's an integer. So how to better explain it? So there are two things. Well, there are four things actually: G value, PR value, X value, and some other stuff too. But mainly we will be focusing on mainly the like not me, but these notes will be focusing on N value and R value. So let's see. Well, the author, I think his name is Alex. Yeah, they will come back to why this is not possible. L value and R value. So so when we say X, when we write this expression, so this is what are the curly braces called? Direct list, direct list was what is it? What was it? I forgot. Initialization in C++. So which is a good principle process. We get very confusing to read your code and additional such people and to just give me a minute. I think it's called direct list initialization. List initial. I'll just look at images. What is this? I should try to. Yeah, let's put this GFG, Geeks for Geeks. Okay, initializing really good. This is, yeah, okay, whatever it is called. So here what is happening is that whenever uh, let's instead of this let's consider this as a simple int x equal to 5. So what happens is that it is the equality sign, so we are assigning a literal 5, like, okay, not assigning to 5, we are assigning x variable a value of 5. So what is happening is that whatever is inside the braces needs to be r value, you can say. So phi is the R value. What is the R value? Maybe they explain it somewhere. Okay, let's consider this. So what is the L value? L value is an expression that evaluates an identifiable object or function. So it is identifiable, and it should possess like more than the line that it is used on. So if I write int x 5, I can still find the value of x. I can still identify x on the next line and get the same value. I cannot do the same with phi. Phi is gone. Boom, vanished. So x is the L value expression. Yeah, boom. Uh, what is what is the next thing? Yeah, R value. So what is R value? R value is everything that is not L value. Boom, easy. So commonly seen R value includes literals except C style string, which are L values. So I'll also tell you like why this is the reason. But let's focus on like why C style string literals are not R values, they are instead L values, even though they disappear, but there is something I will tell you afterwards. So R value is an expression that is not L value. Boom. Wow, very easy. R value expressions evaluate to a value, basically this. So when I write phi, this is the R value expression phi. X evaluates to itself, like x evaluates to a variable x. Boom, this is possible. So what is happening over here when we write x? X is a modifiable value, L value expression. So what we are doing over here is that compiler will change this x to a R value, which is phi, which is the value inside it. So that's what is happening. Const double d, that is fine, that is allowed. D is a non-modifiable L value expression, so this works. So D is an L value expression. 1.2 is an R value, and D is a L value expression. When you write over here, return phi, a function, the function evaluates, like the function call evaluates to R value itself because it's like returning some kind of value. Maybe, yeah, so return phi evaluates to an integer, which is R value. So yeah, that is it. Static cast also evaluates to R value. I think this is getting a bit hectic. Yeah, okay, let's should we do this? Yeah, okay, let's do this. So print phi, so this is R value. Get int, since I said function call is R value. Boom. Int x is declared x is the L value because it is a like it has an identifier x. Stood string hello, it's R value. Now C style string, it's L value. Why? So stood string, which is a C++ string, it it is not allocated any kind of space in the functions in the process memory, right? But hello over here is allocated a memory. You will see like I can hello doesn't have an identifier. It does have an identifier. It's just we don't see it. So whenever so le- okay, tell me. C style strings have like how are they stored? It's a collection of chars, right? It's a char array of chars, and it what is it? It implicitly converts to a pointer to the beginning of the array. So that is what C style strings are. But in order to convert, in order to implicitly convert to a pointer to the starting of the array, it needs to be stored somewhere, and it needs to have an identifier. It's just we don't see it. So hello is stored in read-only segment, something like that. There's a read-only segment of the process. I showed the diagram. Uh, yeah, plus plus x. This is fine. This is the L value because plus plus x increments the x and returns the object, while on the other side R value uh, like it just like returns the value of the x and increments later, right? That is basically that. Plus plus x means increment first and then return the object. X plus plus is like return the value and increment later. Yeah, see, they have talked about this. I was like really shocked when I read about this, like C style DK array. So this is basically like converting to like the initial pointer or something. Yeah, okay. And value references. How many minutes in? 17 minutes in, and we haven't even started something new. I think this might take a few. This might take some time. Should I skip it? Yeah, I've read this. Yeah, pass by value reference. Let's go. Starting something new. In the previous lessons, we introduced L-value references. Yeah, and L-value references to const. Yes. In isolation, these may not have seemed very useful. Why create an alias to variable when you can just use a variable itself? That is pretty uh, like beginner questions. But I know the answer. Like I haven't read this, but I know like there's a thing called pass by value and pass by reference. That's why we use pointers in C and there are references in C++. People say that references are better than pointers, but you know, dangling can still occur in C++, right? C++ references. But okay, let's keep reading. In this lesson, we will finally provide some insight into what makes references useful, and then starting later in this chapter, you will see references used regularly. Okay. For some context, back in lesson boom, we discussed pass by value, where an argument passed to a function is copied into the function's parameter. Yes, correct. Int y. So this creates a copy of the x. So this creates a copy of this variable, which is y equal to 2. Yeah, and y doesn't make it out of the function. Y is destroyed. Y lost its life. So print value, yep, x is passed to value into parameter y, inexpensive. In the above program, when print value x is called, the value of x, sorry, 2 is copied into the parameter y, and then at the end of the function, object y is destroyed. This means that when we call the function, we make a copy of our argument's value only to use it briefly and then destroy it. Fortunately, because fundamental data types are cheap to copy, this isn't a problem. But some objects, like massive ones, like A very, very huge array. That is expensive. Some objects are expensive to copy. Most of the types provided by the standard library, such as string, are class types. Class types are usually expensive to copy. Whenever possible, we want to avoid making unnecessary copies of objects that are expensive to copy, especially when we will destroy those copies almost immediately. Consider the following program illustrating this point. Yeah, so print value, we are instead giving it a string, which is a, uh, what is it? What do we call? It's a string object that is expensive. Um, yeah, it's a class type, whatever. String hello world x, and then we pass this x is passed value copied into the parameter y expensive. Yes. While this program behaves like we expect, it's also inefficient. Identified identically to the prior example, when print value is called, argument x is copied into print value parameter y. Because in this example the parameter is a string instead of an int, and string is a class type, that is expensive to copy. And this expensive copy is made every time print value is called. We can do better, pass by reference. One way to avoid making an expensive copy of our argument when calling a function is to use a pass by reference instead of pass by value. When using pass by reference, we declare a function parameter as a reference type or const reference type rather than as a normal type. When the function is called, each reference parameter is bound to the appropriate argument. Because the reference acts as an alias for the argument, no copy of the argument is made. Hence the same example as above, using pass by reference instead of pass by value. Cool. Yeah, okay. It works like a pointer. I don't see anything useful that a reference provides over pointer, but maybe we'll find out later. So let's keep reading. So I also read that pointers occupy space, right? Like the pointers have some space. Like when we write this, so let's say I so cd or let's say desktop rme.cpp rme.out. Let's see I do this. Oh, my bad. Let's say I do this. Well, I don't initialize my variables like this. I do it this way. Sorry. And let's say I do this. What do we call? Int pointer p is equal to and of x. Can I initialize this with this? Is this allowed? I think it should be. So if I do this, what was I going to do? Yeah, size of p. This should be around 8 bytes, I guess. It should be 4 bytes. Duh. What? What am I even saying? It should be 4 bytes, bro. What? Yeah, okay, my bad, my bad. Yeah, okay. Yeah, 8 bytes because I'm on a 64-bit system and 64 divided by 8, which is number of bits, so I get 8 bytes. I'm sorry, I got confused. I was not sure about uh, what the size of int was. So okay, type change to string and why is this stored here? Yep, sure, cool. So why the stored here? It's just a reference. Okay. Also, I have to confirm another thing. Does reference take up space like a pointer? I've read that reference is just an alias to a variable with existing decimal multiple. Consider the following code. Interlink this, int y, int and z, So this is address of A, which is supposed to be cool 740. If reference does not copy memory in the stack, why is the memory being offset? In the function test, local variable is this. The function has four parameters. Each parameter is used to be passed to a function. The fact that one of the parameters is a reference does not change the basic fact. The additional space receives the reference point out of the function. In this context, the reference is really just a pointer to disguise. When you have a reference in the local scope referencing to an object in the local scope, most C++ components will indeed optimize it away so the reference does not take up any actual memory. The function calls an entirely new ballgame. The function expects to receive a reference to some object. The function cannot know telepathically that is what is being passed to it as a reference. Whatever is calling the function is responsible for supplying the reference parameter. It goes without saying that a few bytes will be needed to pass that information along, namely the address of an object that is passed as a reference. Then mentioned something about pointers recently. Certainly possible that if the function was declared with static scope, no external linkage of the sufficiently aggressive optimization level is selected for a compilation. Your C++ compiler will inline the function call and will be able to optimize the reference parameter array. Cool. I get it. So in the case of function, to answer this question in more general way, the C++ does not require that the reference should occupy memory, but it does not require that they should not. The C++ compiler is free to compile the code in any way as long as the results are correct and what they are expected to be. If in a particular situation, a C++ compiler figures out how to optimize away a reference so that it does not actually exist as a discrete object of its own, it is free to do so, but it is not required to do that. Let me just temporary chat. Are reference do references take up space like pointers in C, or they are just find and replace? Also, pointers when calling a function. It depends on the language. C++, yeah, I was talking about C++. Not find and replace do take space in typically same size as a pointer implemented like pointers by the compiler. Function call passing the reference this cannot be null, cannot be elicited. This yeah, cool. Conceptually alias, physically pointer. Why can't yeah okay. I'll figure that out afterwards. Yeah, cool. Yep, okay. Should string this program is identical to Python, except this. Yeah, I've read that. Pass by reference allows us to pass arguments to a function without making copies of those arguments each time the function is called. The function program demonstrates that a value parameter is a separate object from the argument, while the reference parameter is treated as if it were the argument. Sorry. So void print the following program demonstrates that the value parameter is a separate object from the argument, while the reference parameter is treated as if it were the same argument. Yeah, okay. So int x, the address of x is this. We do this int value, int reference. So this will have a different address. This will have the same one. DE4, boom, a different address, and DE0, which is the same thing. Cool. We can see that the argument has a different address than the value parameter, meaning the value parameter is a different object since they have separate memory address. In order for in order for the value parameter to have the same value as the argument's value must be copied into the memory held by the value parameter. On the other hand, we can see that taking the address of the reference parameter yields an address identical to that of our argument. This means that the reference parameter is being treated as if it were the same object as the argument. Cool. Okay, let's go. So pass by reference allows us to change the value of an argument. When an object is passed by value, the function parameter receives a copy of the argument. This means that any changes to the value of the parameter are made to the copy of the argument, not the argument itself. Are made to the copy of the argument, not the argument itself. Okay. Yeah. Okay. Cool. So if he this is x, cout value of x is phi. Boom. Phi. Add one int y. A copy is created and the copy is incremented and the copy is destroyed over here. So x is not modified. If you print this again, it's still phi. Cool. Let's do this over here. So int x, this is phi, add one. So this is a reference, incremented 6, cout 6. Boom. In the above example, initially x initially has a value. Okay, I don't want to read that. The ability for functions to modify the value of an argument passed in can be useful. Imagine you have written a function that determines whether a monster has successfully attack the player. If so, the monster should do some amount of damage to the player's health. If you pass your player object by reference, the function can directly modify the health of the actual player object that was passed in. If you pass the player object by value, you could only modify the health of a copy of the player object, which isn't as useful. Pass by reference can only accept modifiable L value arguments. Why? Why? So const are static, so they required it to be static. Okay, then let's keep reading. So because a reference to a non-const value can only bind to a modifiable L value, hmm, essentially a non-const variable, this means that pass by reference only works with arguments that are modifiable L values. In practical terms, this significantly limits the usefulness of pass by reference to non-const, as it means we cannot pass const variables or literals. For example, int x, y only accepts modifiable L values. Yup. Okay, x is a modifiable value. Const int z phi, error z is a non-modifiable L value. But if I write const, I shouldn't have deleted the stuff, right? Yeah, okay. So hash include IO stream. Let's say I have domain. So if I write int, uh, I should write const int x is 10, and then I can do call some function. So this is void some function, and it's also const int y. Yesterday cout. I cannot increment it, so only reading is allowed, right? And it's void some function x. Hmm, let's test this. I am just habituated to writing C++17 because I don't want to click it like two times because of my lady finger, boom 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 boom. It's just faster to do something with both hands. So either I could do 2-0, the 2-0, or 117. So 117 just feels better. I'm not using any kind of C++17 feature. Yeah, okay, so this works, but I can't do this, which is super obvious. Yep. What was the error? Yep, cool. Error z is not modifiable value. Error phi is R value. Cool. Oh, I can also do this. This will still work. Yep. Fortunately, there's an easy way around this, which we will discuss in next. This one just convert it to const. What the? Yeah, pass by const value reference. Unlike a reference to non-const, which can only bind to modifiable L values, a reference to const can bind to modifiable L values. L values, non-modifiable L values, and R values. Therefore, if you make a reference parameter const, then it will be able to bind to any type of argument. So this, okay, yep, everything works. Passing by const reference offers the same primary benefit as pass by non-const reference, avoiding making a copy of the argument, while also guaranteeing that the function cannot change the value being referenced. For example, the function is disallowed before because reference is const. Yeah, not allowed. Sure. In most cases, we don't want our function modifying the value of the arguments. Best practice, favor passing by const reference over passing by non-const reference unless you have specific reason to do otherwise. Example, the function needs to change the value of the argument. Cool. Now we can understand the motivation of passing const L value references to bind to R values. Without that capability, there would be no way to pass literals or the R values to functions that can be passed by reference. I think there should be a site called C++ by example. I think there must be a site. This is so much better. But okay, it's fine. I'm reading in depth. I actually like the light version. Should I continue in this? No, okay, we'll change it. Okay, so yeah, now we can understand the motivation for allowing const. It's 38 minutes in. Okay, cool. Audible, recording. That's cool. Now we can understand the motivation for allowing const and value reference to bind to R values. Without that capability, there would be no way to pass literals or other R values to functions that use pass by reference. Passing arguments of a function different of a different type to a const and value reference parameter. Is that allowed? Let's test. Let's test it ourselves first. So let's say this was, oh, it's possible. So even if it's const, it works. Cool. It works. Wait, where am I? Yeah, okay. We noted that a const and value reference can bind to a value of a different type as long as that value is convertible to the type of the reference. The conversion creates a temporary object that the reference parameter can then bind to. Oh yeah. It creates a temporary object. It's not the same thing. So there was that. Okay, it was in the previous one. So let me check that out. Uh, just let me do some stuff. Was this it? Extend the modifier value just to modify the const in. No, not this one. The example row digital. Yeah, okay. Yeah, I think this is it. Yeah, okay. So double R1 5. So this is fine. Temporary double initialize with value of 5. R1 binds to temporary. So there's temporary stuff, prints phi, cool. C is A, R to C, temporary int initialize with value A, R to minus temporary. So let me show you what they're talking about. So let's say if I do this, verify, write, let's say char C is A. So then let's say this is it. And then if I do int, that int is fine. So int I is the difference of C. Cool, cool. So if I do std cout I, this will print out 97. If I do std cout C, this will still do um, 97. Yeah, because it converts to int, maybe. But let's say I modify this. Boom. What do you think the reference will, what do you think the answer will be? Non-constant value reference to type. Oh, yeah, yeah, yeah. It should be const. It's supposed to be const because of some reason. So I can't modify I. I can modify C though. Boom. Did you notice that? So what happened is that, so the output is this. So let me just copy this. So what happened is that C is small a. So an I is a const reference of C, which is um, like implicitly converted. So what happened is that C out I prints out the reference value. C prints out the char value, like what the char is, and then we increment C. So you will see like if we are incrementing C, then the reference should do the same thing, right? Duh. But the reference is bound to a temporary form of C. Like it's not the real C. So even if we modify C over here, the reference still prints out 97, which was correct, but the C has been modified, which is B. You getting me? So yes, that was it. Okay, the conversion creates a temporary object that the reference parameter can then bind to. The primary motivation for allowing this is so that we can pass a value as an argument to either a value parameter or a const reference parameter in exactly the same way. So this, yeah, okay. Print value phi. So if we do this, print value phi. So print value phi. So double goes over here. It's double implicitly converted. It will still show up as phi. So this is fine. And if we do this, const double t, it's still this. Cool. What if I do a function? So void some function. If I do this, where it takes in, will this work? No. No matching. Boom. Cool. Char to int for first argument. And if it's const, it will work. Okay, bound to parameter D. With pass by value, we expect a copy to be made. So if a conversion occurs first, resulting in an additional copy, it's rarely an issue, and the compiler will likely optimize one of the two copies away. Often we use pass by reference when we don't want a copy to be made. If conversion occurs first, this will typically result in a possibly expensive copy being made, which can be suboptimal. This type of reference actually result in an unexpected and possibly expensive conversion. Cool. So even if we are passing like we are thinking like, oh, it's 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 a reference. No, it's not at all expensive. It's cheap, but it still will create a copy if the types don't match. So that's why the warning with pass by reference, ensure the type of the argument matches the type of the reference, or it will result in an unexpected and possibly expensive conversion. Mixing pass by value and pass by reference, a function with multiple parameters can determine whether each parameter is pass by value or reference by reference individually. For example, void foo, int a and b, string c, cool, phi this. The first argument is passed by value, the second by reference, and the third by const reference. Here, even if we did, uh, even if it is not const, this will still work, right? Yeah, it still works. When to use pass by value versus pass by reference, for most C++ beginners, the choice of whether to use or pass by value isn't very obvious. Fortunately, there's a straightforward rule of thumb that will serve you well in the majority cases. Fundamental types and enumerated types are cheap to copy, so they are typically passed by value. Class types can be expensive to copy, something significantly so, so they are typically passed by const reference. Best practice, pass fundamental types by value, class types by const reference. If you aren't sure what to do, pass by reference as you are likely to encounter unexpected behavior. Okay, here's a partial list. Enumerator type, unscope and scope enumerations, views and spans. Cool. This, don't know most of the stuff. Pass by reference. Yeah, OS string. This is expensive. It's the file stuff. The stuff inside the file copyable. Ownership. Oh, the types where copying has ownership implications that we want to avoid. Beauty pointer, shell pointer. Ooh, cool. How much more? Well, that's big. Okay, we'll cover that. That's fine. No big problem there. The cost of pass by value versus pass by reference. Not all types need to be passed by reference, such as string view. So this is advanced. Not all class types need to be passed by reference, such as string view, which is normally passed by value. And you may be wondering why we don't want to pass everything by reference. In this section, which is optional reading, we discuss the cost of pass by value versus pass by reference and refine our best practices as to when we should use each. First, we need to consider the cost of initializing the function parameter. With pass by value, initialization means making a copy. The cost of copying an object is generally proportional to two things: the size of the object. Objects that use more memory take more time to copy. Any additional setup cost. Some class types do additional setup where they are instantiated, such as opening a file or database or allocating a certain amount of dynamic memory to hold an object of a variable size. These setup costs must be paid each time an object is copied. Okay. On the other hand, binding a reference to an object uh, is always fast, about the same speed as copying a fundamental type. Mm. Second, we need to consider the cost of using the function parameter. When setting up a function call, the compiler may be able to optimize by placing a reference or copy a pass by value argument. If it is small in size, into a CPU register. Second, we need to consider the cost of using the function parameter. When setting up a function call, the compiler may be able to optimize by placing a reference or copy of a passed by value argument. If it's small in size, into the CPU register, which is fast to access, or RAM, which is slow to access. Each time a value parameter is used. Okay. Mhm. Got it. Each time a value parameter is passed, the running program can directly access the storage location, CPU register or RAM, of the copied argument. However, when a reference parameter is used, there is usually an extra step. The running program must first directly access the storage location, CPU register or RAM, allocated to the reference in order to determine which object is being referenced. Only then it can access the storage location of the reference type. Yeah. Okay, cool. Therefore, each use of a value parameter is a single CPU register or RAM access, whereas each use of reference parameter is a single CPU register plus a second RAM access because of the reference. Third, the compiler can sometimes so whenever there is a small data type, let's say short, int, long, the fundamental ones, we just pass by value. That's it. So third, the compiler can sometimes optimize code that uses pass by value more effectively. Third, the compiler can optimize that uses Third, the compiler can sometimes optimize code that uses pass by value more effectively than code that uses pass by reference. In particular, optimizers have to be conservative when there is a chance of aliasing and to more pointers of reference right? Okay. Because pass by value results in the copy of argument values, there is no chance of aliasing to occur, allowing optimizers to be more aggressive. We can now answer the question of why we don't pass everything by reference. For objects that are cheap to copy, the cost of copying is similar to the cost of binding, but accessing the object is faster and compiler is likely to be able to optimize better. For objects that are expensive to copy, the cost of copy dominates other performance considerations. Cool. The last question that then is how do we define cheap to copy? There is no absolute answer here as this varies by compiler, use case, and architecture. However, we can formulate a good rule of thumb. An object is cheap to copy if it uses two or fewer words of memory, where a word is approximated by the size of the memory address and does no setup cost. Word is approximated by the size of the memory address. There's no setup cost. Okay. The following program defines a function like macro that can be used to determine if a is cheap to copy accordingly. Okay, let's see. Yeah, it's a void. Yeah, cool. If it's more than twice of this, do it. Which is 16, right? Bood alpha, cool. It's small. This will be expensive. So it's small. Int just it's small. Yeah, it's small. D, which is double, it's still small. S, that's expensive. False. As an aside, we use preprocessor function like macros here so that we can provide either an object or a type name as a parameter. And C++ function disallows passing types as a parameter. We use a preprocessor function like macro here so that we can provide either an object or a type name as a parameter. Yup, as C++ disallows passing types as a parameter. Yeah. However, it can be hard to know whether a class type object has setup costs or not. It's best to assume that most standard library classes have setup costs, unless you know otherwise that they don't. An object of type T is cheap to copy if size T is less than or equal to this and has no additional setup cost. For function parameters prefers stood string view over const stood string and in most cases. Why is that? One question that comes up often in modern C++ when writing a function that has string parameter: should the type of the parameter be string and or string view? In most cases, string view is better choice as it can handle a wider range of arguments types efficiently. A string view parameter also allows the caller to pass in a substring without having to copy that substring into its own strings first. Huh, right. Yeah, yeah, yeah. Nice. There are a few cases where using a const, am I recording? Audible, recording. There are a few cases where using a const, std string, and parameter may be more appropriate. Yeah, okay. If you are using C++ 14 or older, string view isn't available. Hmm. If your function needs to call some function that takes a C style string or std string parameter, then const may be a better choice, as string view is not guaranteed to be null terminated, something that C style string functions expect and does not effectively convert to a string string. Cool. Best practice: prefer passing the strings using string view by value instead of this, unless your function calls other functions that require C style strings. Yes. Why string view parameters are more efficient than this? Advanced. In C++, a string argument will typically be std string, a std string view, or a C style string literal. As reminders, if the type of argument that does not match the type of the corresponding parameter, the compiler will try to implicitly convert the argument to match the type of the parameter. Cool. Converting a value creates a temporary object of the converted type. Creating or copying a std string view is inexpensive. That string view does not make a copy of the string it is viewing. Creating or copying a std string can be expensive as each std string object makes a copy of the string. Here's a table showing you what happens. So std string view parameter inexpensive conversion, reference binding. No. So string view, inexpensive copy, expensive explicit conversion to std string. Okay. C style, inexpensive, expensive conversion. Cool. With a std string view value parameter, if we pass in a std string argument, the compiler will convert std string to string view, which is inexpensive, so this is fine. If we pass in a std string view, the compiler will copy the argument into parameter, which is inexpensive. It will just copy. If we pass C style string, the compiler will convert these to string view, which is inexpensive, so this is fine. As you can see, std string view handles all three cases inexpensive. With const, std string, and reference parameter. Okay, so with a const, std string, and reference parameter, if we pass std string, the parameter reference bind, which is inexpensive, this is fine. Yeah, this is fine. If we pass in a string view argument, the compiler will refuse to do an implicit conversion and produce a compilation error. We can use static cast, so pass string view, and I'm going to convert to this. This gives us an error. We can use static cast to do an explicit conversion to string, but this conversion is expensive since std string will make a copy of the string being viewed. Once the conversion is done, the parameter will reference bind to the result, which is expensive, but we have made an expensive copy of the conversion, so this is similar to great expensive copy. If we pass in a C style string literal, the compiler will implicitly convert this to std string, which is expensive. Hmm. So this isn't great either. Only handles this inexpensively. The same in code form. So and this is string. String view is for s. Cool. Print sv. Sv is string view, and this is just reference string view. S is parse, inexpensive code. Then we pass a string view. It just creates a copy of the SV when we are calling this SV. Hello world, C style string, inexpensive conversion to this, string view. Inexpensive, compile error because then we have to explicitly convert. So this is explicitly conversion, static cast, so string SV, explicitly converting the string view to a string, and then again, this is like the passing the reference, explicit creation of the string string. And this is bad, explicit creation of string temporary. Yeah, this is temporarily stored somewhere. As I said, C-style strings are stored in temporary read-only memory. Additionally, we need to consider the cost of accessing the parameter inside the function. Because a std string view parameter is a normal object, the string being viewed can be accessed directly. Plus, an additional step to get the referenced object before the string can be accessed. Wait, because a std string view parameter is a normal object, the string view being viewed can be accessed directly. Because a std string view is a normal object, the string being viewed can be accessed directly. Accessing a std string and parameter requires an additional step to get the referenced object before the string can be accessed. Okay. Finally, if we want to pass in a substring of an existing string of any type, it is comparatively cheap to create a string view substring, which can then be cheaply passed to a string view parameter. In comparison, passing a substring to a is more expensive substring. Okay, cool. So we have completed strings and references, and now we will be reading about pointers. But before that, we'll take a break of 5 minutes. I'm not going to sleep. I'm not going to sleep. Hello, hello, welcome back. So, the break was not enough. I'm still feeling a bit tired, but it will be nice to complete like a lot of like. Just think about it. We are able to complete the entire chapter 12 in just a single video. That will be great, right? But I'm not sure if I can do this like 12.7. I've completed till this, but I'm not sure. Even just doing the two chapters took a lot of time. It's 1 hour. This might take us more, but they're pointers. I can skip a lot of the stuff because I've already made a I've already like my body is 25% pointers. Uh, because I've made the memory allocator project. A lot of pointers, pointer arithmetics, and a lot of stuff. I know some stuff like from pointers, so uh, I think I should. Okay, how about this? I'll take a little bit longer break of maybe 5 or 10 minutes, and I'll be back. Okay, so this is 1:08, right? I'll be back at 1:13. So I'm not ending the video. Okay. Hello, hello. Recording, recording, record. No, see. Audible, audible, audible. Recording, recording, recording. Cool. So we have completed 12.1 to 12.6, and let's start with the pointers. Let's go. Oh, okay. So first chapter says you. Oh my God. Sorry, scary. I must search on. Okay, so this is going to take some time, but let's continue. Pointers are one of the C++ historical boogeyman, and a place where many aspiring C++ learners have gotten stuck. However, as you will see shortly, hello, hello, hello. You will see shortly, pointers are nothing to be scared of. In fact, pointers behave a lot like L-value references. But before we explain that further, let's do some setup. You will be good time to do this. Fine, sure. Consider a normal variable like this one. Char x this. Char uses 1 byte of memory. Simplifying a bit, where the code generated by this definition is executed, a piece of memory from RAM will be assigned to this object. For the sake of example, let's say the variable x is assigned to a memory address 140. Whenever we use the variable x in expression or statement, the program will go to the memory address 140 to access the value stored there. The nice thing about variable is that we don't need to worry about what specific memory address are assigned or how many bytes are required to store the object's value. We just refer to the variable by its given identifier, and the compiler translates this name into appropriately assigned memory address. The compiler takes care of all the addressing. This is also true with references. So ref is an L-value reference to X when used with a type and means L-value reference. Because the reference acts as an alias for X, whenever we use a ref, the program will go to the memory address 140 to access the value. Again, the compiler takes care of the addressing so that we don't have to think about it. The address of operator. All the memory address used by variables aren't exposed to us by default, so we don't have access to this information. The address of operator returns the memory address of its operand. This is pretty straightforward. So x is the memory address. In the above example, this numeral systems often with the prefix 0x. Yeah. The and symbol tends to cause confusion because it has different meaning depending on the context. The following A-type name and denotes a value reference. Yep. This is also the AND of address of operator and bitwise AND. Cool. The dereference operator. Getting the address of a variable isn't very useful by itself. The most useful thing we can do with the address is access the value stored by the address. The dereference operator, also occasionally called the indirection operator, returns the value at the given memory address as an array value. So this, yep, cool. Cool. Parentheses are not required, but makes it easier to read. Cool. Yep. First, we declare the variable x and print its value. Then we print the address of the variable x. Then we use the dereference operator to get the value of the memory address of variable x, which is just the value of x which we print to the console. Key inside given memory address, we can use the dereference operator to get the value and that address as an L value. The address of operator and a dereference operator work as opposites. Address of gets the address of the object, and dereference get the object of get the object at the address. Although the dereference operator looks just like multiplication operator, we can distinguish them because the dereference operator is unary, whereas the multiplication operator is binary. Yep. Getting the memory address of a variable and then eventually dereferencing that address to get the value isn't that useful either. After all, we can just use the variable to access the value. But okay. But now that we have the address of operator and the dereference ordered to our toolkits, we are ready to talk about pointers. A pointer is an object uh, that holds a memory address typically of another variable. as its value. Just give me a minute. Hello, hello, hello. Uh, recording, recording, recording. Back again. Let's go. A pointer is an object that holds a memory. Wait. Okay. A pointer is an object that holds a memory address, typically of another variable, as its value. This allows us to store the address of the same. I think I should drink water. I'm so sorry, but another break. Look at my face. Hello, hello. Oh, I forgot to mute myself. Okay, cool. Audible, audible, audible. Recording, recording, recording. Cool. Let's go. So, uh, this allows us to store the address of some other object to use later. As an aside, in modern C++, the pointers we are talking about here are sometimes called raw pointers or dumb pointers to help differentiate between the smart pointers. Yeah, they were introduced into the language more recently. Yeah, smart pointers and unique pointers. The unique pointers, share pointers, those kind of things. We cover smart pointers in chapter 22. We are going to look at that eventually. A type that specifies a pointer, example int asterisk, is called a pointer type. Much like reference types are declared into a ampersand character, pointer types are declared using the asterisk. So int, a normal int, this is the reference to an int value, and a pointer to an int value holds the address of the integer value. To create a a pointer variable, we simply define a variable with a pointer type. Yeah, it doesn't need initialization, by the way, and it can be modified. Note that this asterisk is part of the declaration syntax for pointers, not a use of the dereference operator. When declaring a pointer type, place the asterisk next to the type name. Okay, cool. Although you generally should not declare multiple variables on a single line, if you do, the asterisk has to be included with each variable. Incorrect, pointer 1 is a pointer and pointer 2 is just a normal int. Yeah, I know that. But I just don't like the syntax. Although this is sometimes used as an argument to not place the asterisk with the type name, instead of placing it to the next variable name, it's better argument of avoiding defining multiple variables in the same statement. Yeah. Pointer initialization. Like normal variables, pointers are not initialized by default. Yeah, okay, like normal variables, pointers are not initialized by default. A pointer that has not been initialized is sometimes called a while pointer. A while pointer contains a garbage address, and dereferencing a while pointer will result in undefined behavior. Because of this, you should always initialize your pointers to a known value. Always initialize your pointers. Cool. Sorry. Int main x boom boom. Yeah, okay. Pointer, you can do this too. It's just a null. An uninitialized pointer holds a garbage value. A null pointer, we'll discuss in next lesson. A pointer initialized with variable with address of x. Since pointers hold addresses, when we initialize or assign a value to a pointer, that value has to be an address. Typically, pointers are used to hold the address of another variable, which we can get using the address of operator. Once we have um, let's try something. Hey, I don't like this. I don't like this either. So let's say I do this. Let's do pointer ptr is equal to yep. Once we have a pointer holding the address of another object, we can use the dereference operator to access the value. This so cout x this print the value of variable this get the address dereference it get this. Look at this dude. Yeah, okay. Conceptually, you can think of the above snippet like this. So this is a pointer, by the way, a pointer has its own address. So let's say if I write this, so int a is 10, int b is a pointer b, int this and a yesterday cout a. So let's say I do this address a student l. There's also a, let's say dereferencing b. I should do the a and then address of a then B, and then address of B. How about that? Cool. So the values are different. You can see this one too. So this is the value of B, and this is the address of A. Address of A and B is the same thing, but the B, which is a pointer pointing to A, it has its own address. Okay, it has its own address, bro. I'm telling you, it has its own address. And why was that address smaller? Why did this happen? 3784 and 3776. Hello. Right, it's on the stack. I forgot. Oh, sorry. And also the order doesn't matter. Okay. Okay. Note on pointer nomenclature. X pointer when X is some type. It's a common. I don't need this. So int I double D. Okay, a pointer to an int. So this is a pointer to an int. Pointer D. What was the site where we can take a quiz and know about how much I know about pointers? Okay. So yeah, okay. I pointed to an int object. I pointed to address of D. Not okay. A pointer to an int can't point to a double object. Yep. And this okay. A double pointer pointing to a double fine, and I not okay. With one exception that we will discuss next, initializing a pointer with a literal value is disallowed. Yep, definitely. As a pointer, it wants an address. Not okay too. It's treated as an integer literal. Oh, okay. Pointers and assignment. We can use assignment with pointers in two different ways. To change what the pointer is pointing at by assigning the pointer a new address. To change the value being pointed at by assigning the dereference pointer a new value. First, let's look at a case where a pointer is changed to a pointer at a different object. To change what the pointer is pointing at by assigning the pointer a new address. To change the value being pointed at by assigning the dereference pointer to oh I just can't focus, bro. I'm so sorry. I just can't focus right now. Okay. Yeah, this is a lot. I think I should have ended the video like earlier. Uh, well, okay. This has been a great video. Thanks for watching this video. I'm Vidya Bachani and I am an engineer for fun. Bye.